Hello everyone, I am Giuseppe Maggiore. Welcome to the Introduction to C#. Today we continue lecture 9, or at least lecture in the sense of we continue talking about generics, which is lecture 9, and the second part of this lecture talks about generic operations. Until now, in lecture 9, we talked about generic containers, which is perhaps the most obvious application of generic types in C#. Now we graduate not just to containers that contain data as in a box where you put stuff, like a box with things, but rather something that differentiates computing from the physical universe. That is, that in computing we can also represent operations. So generic operations, lambdas, and tasks in particular, are containers because you can do something that is equivalent to saying open the box and get the value out of it, but as you get the value out of the box, the value will materialize. So the value was not in the box, but the act of fetching it from the box generates the value in a sense. And this is quite exciting. This is very similar to what we did with yield return, which is a way to dynamically generate a collection, and lambdas and tasks are ways to dynamically generate values. All right, now let's clean up the remainders of the previous sample. All right, so C# is a language that supports higher order functions. Or what does it mean? It means that it can manipulate references to functions in variables, parameters, fields of classes, etc. And this is done by means of a specific type. So the type of a function that takes as input, let's say an integer, and returns, let's say, another integer, is the generic type func, and then between angle brackets, int to int. Or we could say string to int, for example. So this is a function that takes as input a string and returns an int. Or function person to int, or function of list of int to int, and so on. Actually, why not? Let's say that we have a function from immutable list of int to int. Why not? Such a function, of course, needs a name. Let's say that this adds all even elements, for example. Let's give it a little body, and then with equal we can simply decide, okay, now I want to specify what is the value of this function. So this is the type, the generic type of a function, and now we can have the body of a function, the expression of type function. Okay, now we take as input the list, and then what do we do with this list? Well, let's say that we only keep all the values. Oh, okay, this is very useful actually. We keep all the values which are even, and then we add all of them together. There you go. Now, what can we do with something like add even? We can call it, and you can see that in the suggestions that we get the advice, well, pass an immutable list of int. So immutable list dot empty. No, the autocorrection is really fighting against me right now. Of course, it's an immutable list of int.empty, to which we add, for example, 0, and then we can add 1, and then we can add 2, etc. Well, actually, let's do this recursively. So a lot more fun. Okay, so let's say that we have a function that adds all the elements up to. So range until. Okay, very good. Let me think. No, let's say range between. Okay, so this will be a function that creates an immutable, that takes as input the lower and the upper bound of the range and returns the immutable list between that range. So we take as input the lower and upper values of the bound, and then if the lower bound is greater than the upper bound, well, then there is nothing to do. so immutable list of int.empty. Otherwise, what do we do? Well, we get the range from L to U minus 1, so we get almost all the range minus the last element, and to this we add the last element. Oh, so unfortunate. Well, the type is okay, but we cannot really do this. We cannot really. What a disappointment. Well, it doesn't matter that much, because it's a recursive function, and then we cannot have recursive lambdas. Okay, yeah, whatever. Close enough. But now, at least worked. So now we can call range until. Let's say from 1 to 10, and then we're adding all values between 1 and 10, which are even. So 2, 4, 6, 8, and 10 itself. And let's try to run this little program. Nothing blows up. We might also want to print, of course, console.writeLine the result of add even. Okay, we get 30. I honestly have no idea. I honestly have no idea if 30 would be a reasonable value for this. Let's actually print this. Let's print the list. Let's see if everything is going as we expected. So add even of, and then the list results in, and then this value. Well, close enough. Can we just join? No, this is the wrong kind of join. String.join. Then we get a separator. Let me see. Yeah, so the separator will be a comma, and the values will be this to an array. Okay. Join is a fantastic way to actually turn a collection into a string with a given character as a separator. So now we should see something a little bit better. Well, there you go. At even of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 30. So very quickly, 2 plus 4 is 6, plus 6 is 12, plus 8 is 20, plus 10 is 30. Okay, very good. Nice. A pity still that in C# anonymous function variables cannot be recursive, but you know, as I said already many times, these innovations that come from functional programming, like lambdas, generics, etc., they have been part of the language for relatively a short time. With every iteration, C# becomes more functional, so eventually it will simply be possible. Very good. Now, you might wonder, what is the point of having variables that can store functions? And it's a fair question, especially if you're a beginner. Well, storing functions into variables or other data structures is the basis of dynamic plugin systems. And those dynamic plugin systems make all the difference in the world, because sometimes you just want part of your program to be determined by the end user input. A lot like browser plugins or modding video games through engines where you have some customizability, etc. So let's say, for example, that you have a series of possible operations, a sort of calculator application where we can easily extend our program to support different operations that are triggered by the user input. Now, this is in the console, so it's all quite primitive, the selection of the plugin, but you should be able to see what I mean by the fact that the main logic of the program and the little modules are neatly separated, and we can extend the modules without extending the main logic. So say we have a series of functions. One is add, takes as input x and y, and just returns x plus y. Simple calculator, so the operations will be quite trivial. Subtraction, x minus y. Multiplication, x times y. And division, x divided by y. Okay? Then we put the operations in a dictionary. So this will be an immutable dictionary because we want to store the operations by name. So this will be string and a function from int to int to int. And in this type, function int, we can fit we can fit our add, sub, and mul operations. And now I can say, okay, plus is connected to function add. Minus is connected to function sub. Times is connected to function mul. And finally, if the intelligence allows me, no, I have to keep it. Oh wow, it guessed correctly, at least, very good. And that's it. So this operations dictionary connects basically our main logic. The logic will be based on operations without knowing exactly what the content of operations is. And then these here are our plugins that we could move to another file, load from DLLs dynamically, whatever, and make reasonably and more or less fully customizable. We don't even need to have these functions defined like this if we don't want to use them anywhere else. So we could easily say, no, just put the function value, this is the value of the function here, and the functions will only exist in the dictionary. I find this actually secretly pretty sexy in terms of code organization, so I'm going to do this also because, as you can see, I get to delete a lot of annoying type declarations, which I'm a little bit allergic to, because they are inferred from the context. Because here in this lambda, so the value that I'm putting into the dictionary, the types of the inputs, outputs, of the input parameters and the output of the function are forced to be func int, so I don't need to have any of these pesky declarations that are just distracting. And off we go. So if you ask me personally, this would be my favorite variant of the code, but of course if you need to also use these plugins directly, these functions like add, sub, etc., then this doesn't make any sense. Then you need to keep declarations, but if you only need to have them dynamically available as little plugins, well, obviously then they can stick to this. Alright, so now we can let the user pick the function they want to run by name. So we could say please, which operation would you like to perform? Then we read a line. And now we can say, okay, let's get, this is the operation name. Then the operation itself will be operations of operation name. This could fail, so first of all, let's say that we also have an empty variant in case read line gives us a null for some reason. It's unlikely, but it's not impossible. Then we get inputs. Input 1, then int.parse. Okay, so this thing can crash very badly, so in this case you can imagine there needs to be plenty of error handling logic. I will not add the error handling logic for the parsing of the integers, because we've seen that already, but I will add it for the operation name in a moment. Okay, now, for now we're assuming we have the operation, so now we can simply show console.writeLine, and now I can say input 1, operation name, input 2, results in operation. Now I can actually call the operation, because you see this is just a function int. Input 1, input 2. Now I can run this. Which operation would I like to perform? I would like to perform a sum of 5 and 6, and there you go, I get 11. Now let's try this again. Which operation would I like to perform? Times of 2 and 4, and I get 8. Oh, this is brilliant. Okay, and I can easily extend this. I can say, okay, I also want exponentiation, so other language. I can call math.pow, x to the power of y, and then we just cast this to int, and off we go. So now I have another operator. I can say which operation would like to perform. Well, no, the international keyboard. Okay, let's see if I can just copy and paste it. Okay, 3 and 4. and 3 to the power of 4 is 81, which seems just about right. Okay, of course we would, as always, need to check if operations contains key operation name. Then we do all of this safely. Otherwise, we should simply say that the requested operation operation name is not available. Let's run this. So this is the safe version. So that we have the modulus operation, the requested operation modulus is not available. Now, we're assuming that all operations are binary. So are operations binary operations? Yes, that is the correct word. So they take 2 inputs. But we could have different operations that take different inputs, and how would we achieve this? Well, we could achieve this by using polymorphism. So here, instead of saying we have a function of int, we could say no, we have either binary operations or unary operations that just take 1 parameter, and then we can disambiguate. And in order to do this, we could say that we have an interface. Operation doesn't really do anything. Then we have a record binary int operation, and this simply contains func int, which is the operation itself. But then we could have a unary int operation that just takes 1 int and returns a single int. We could then say, okay, this contains an I operation, so new binary int operation, of course. Oops, sorry, wrong place. Why is it unhappy? Oh, of course I need to state that my binary and unary operations both support, of course, they both have to support clearly implement I operation, otherwise we cannot make things polymorphic. Let's say that the minus operator just flips the value. So just takes its, no, so this we will make a unary int operation and return minus x. Don't be distracted too much by the operations themselves. So now what I'm trying to show is that we can combine multiple lambdas with different arguments so that we can have different plugins, and the plugins can actually have a different lambda thanks to polymorphism. So we're actually seeing plenty of things play and interact nicely together, which, if you ask me, again, very exciting stuff. Even though we've assessed already, I'm easily excited by these computing things. Anyway. Okay, so now we get the operation. We can't really run the operation. Stronger yet, we don't even know how many parameters are actually needed. Well, 1 is always needed, so you know what? I'm going to just read the parameter, the first one, but in order to decide whether or not we read the second parameter, we're going to first switch over the operation. And if the operation is a binary int operation, let's call it B, then we have to break, okay, oh, yes, colon, alright, and in case of a unary int operation, let's call it U, the unary operation, then we know what to do. And in case of default, this really shouldn't happen, so we just break, we don't do anything, but, well, operations are either binary or unary in our case. In the case of binary operation, then we do read the second input. And now, well, we don't work on the operation, but we work on b dot operation, which actually happens to be correctly binary. In the case of a unary operation, then we simply say operation name applied to input 1, and this is u dot operation, which does not take 2 parameters, only takes 1. And if I say minus, I type 10, bam, I don't need to type the second parameter, I simply get that minus 10 is equal minus 10. Okay, well, I hope you can see what this really is about. When it comes to lambdas, there is basically a whole world of things that lambdas support. Let's see the two most interesting. First of all, closures. Lambdas look like they are just functions that you can put in variables, and that is true, but it is only the beginning of the story. Lambdas can also carry data implicitly in the form of what we call a closure. Let me show how this works, and also how the debugger shows it, because closures are such an important concept that they're actually visible via the debugger. Okay, so let's say that we have a bunch of values. So, and this is an immutable list of, let's say, integers. We create the empty immutable list, we add a range, and the range will be, well, let's just create it from 0 to 10, for example, to 10. Yes, okay. All right, so we have a bunch of values. Now, let's define the following slightly weirdly looking lambda. Print sum, which takes as input a bunch of values, which is an immutable list. Let's call it the source. You can even call it values, actually. There shouldn't be any overlap, because this is just scoping, so the same variable can be redefined. And then what do we return? Or let's say that print the sum of the even values. Well, let's make it a little bit spicier. Then we say values.where the value is even, and then yeah, we just add all the values. All right, and we want to print this. So console.writeLine of these values. Actually, I'm never really a big fan of printing and calculating the result and printing it from inside a function, because I think this doesn't really add a lot of value to the logic. Just keep the printing separate, because eventually you would want to split the calculation of a result from consuming this result, be it printing or anything else. But for now, we will not care. Okay, so first of all, what is print sum even? Well, this is a carried function. It's a function in stages. It takes as input one parameter, but then it returns a function that stores this parameter inside. It's a sort of runtime context, and this context is the closure, and then the function expects, well, in this case, no other parameter, but we are separating the function into two stages. The first stage actually gets a parameter, the second stage actually invokes activates the actual calculation. We could also have a parameter here, so we could say print sum modulus, and then divisible by, and then we could say first we take the values, then we take the divisor, and then we say modulus divisor, for example. Well, it's actually a fun variation. All right. Now let's define a function f, which invokes print sum divisible by, and we just pass the values. Okay. What is happening? Now, this is not printing anything, so if I were to run it, nothing really happens. Why does nothing happen? Well, because we just stored the values inside f, but because we haven't provided a divisor yet, and divisor is the next argument, this never happens. Okay. Now we can call f, and we say, okay, print the even numbers. And let's actually run this. And what happens? Oh yeah, okay, I have no clue whether or not this is this is what we're looking for. So let's say 0 to 7. So this will be 0 plus 2 plus 4 plus 6, which is 12, as the machine confirms. Very good. Okay. Let's look at this through the eyes of the tiger, through the eyes of the compiler. Let's start this with debugging. We stop here. Now, print sum divisible by. This is, well, basically just a function. F, on the other hand, It says, okay, it's a method, blah, blah, blah. So it's an invocable thing. The type is action of int. It's not func. Why? Because it doesn't return anything, because console.writeLine returns void, so it doesn't return anything. This is not a func, it's an action. And it takes an int because that's the divisor, it takes a parameter. But lo and behold, it has a target, and the target has values, and the values is an immutable list. And these values are the argument that was passed to the immutable list is stored inside f as a context. So let's say that let's rename this to f1. Rename symbol. Let's call this f1, and then we create, say, f2. And now we pass other values. Honestly, I don't know why I've even declared the variable. We don't really need it. And here it will be from 3 to 11. Okay, so these are two different instances of the same function print sum divisible by, but with different values. So what happens if we start a debugger and we take a look at the target, or better yet, the closure of f1 and f2? Now f1 has a target object which contains the context that the function has acquired so far in the form of parameters that have already been specified as arguments and other variables that were defined in the parent scope. Here we have the values 0 through 6, very good. But if we look at f2, the target values are 3 through 13. Oh yeah, sorry, 11 is the length, so it's not 3 to 11, but it's 11 steps starting from 3. Okay, very good. So you can see that lambdas contain two things. They contain a target object which gathers all the information that is required in order to calculate this body, and in our case the values are required and the divisor also, so the values and the divisor are both candidates to end up in the target object, in the closure. And of course the code, the source code itself of this expression or the body of the function. So the two things, data and an operation. So in a sense, lambdas, it's kind of funny because they contain data, the closure, and one operation. So it's like classes with fields, that's the closure, and just one method, which is the primary method, which is kind of the do your thing method. Yeah, I really like it. Okay. Let's go back to this previous version though with the values, and let's say that, okay, so we call f1 with 2, but then we reassign the values. And now we get 0 through 100. All right. Again, let's start the debugger. And if you look at f1, target values, it's still 0 through 6. Now this is very important because imagine there's a lot of code here. So line 12 is not just a one comment with 3 dots, but it's a lot of code. Maybe there's even multiple files separating line 10 and line 13. So these two invocations of f1, they belong to separate files. It's going to be really tough to debug things that derive from the fact that values has changed. But because values is in the closure and values is immutable, you guessed it correctly, f1 in its closure still refers to the original values that was defined on line 7. Now, let me show you what happens if we take this range and we turn it into a regular list. And remember, list is mutable. Actually, let's turn this into an enumerable, and then here we say values, whatever, we just add more values. We say add range. Okay. Now, what do you think happens? It would be awesome to actually have you guys here in a classroom with me, because it would be nice to actually have a conversation about this. But yeah, what happens is the value has changed, because now the target still refers to the values, but because these values are mutable, And basically, they changed from under our proverbial butts. And the thing is, imagine you're pressed for time. There's a bug. Your project the project manager is in a corner crying. The customer is calling because, yeah, we need the bug fixed, production problems, blah, blah. And you just see these two lines, 10 and 13. So, well, it's the same call, same function, with the same argument. Should give the same result. You're not going to think about it very easily, that there might be a mutable closure in there which is changing because someone thought that the thing was supposed to change. So, I think this is an interesting example that not only shows closures and also these nested arrows, this currying, this partial application, but it also illustrates a little bit why is immutability actually quite neat in order to make sure that calling the same function with the same parameters twice gives the same result. Lambdas can do even more. Lambdas support seamless function composition. So if you have two functions and the output of one is equal to the input of the other, you can just plug them together. Like, imagine that these were actually, if input, output, and if the input of this is the same as the output of this, probably turn around, then you can join them together. You have one input, one output, and of course you have an intermediate passage of data, but that can be sort of smelted into just one invisible implicit operation. Now, let me show you how this works. So let's say indeed that we have one function, let's call it f. I'm really not going to bother about the name of the functions here. This takes as input a bunch of integers. Let's call it, our integers, and gives us L.sum. Oh, and that's it. So this adds a bunch of integers together. And then we have function g, which takes as input an integer, x, and returns whether or not x modulus 2 is equal to 0. Okay? So what are the types of these functions? Well, we can actually write it out. This is a enumerable of int to int. Notice that we can then drop this declaration because it's superfluous. I actually do like this. I think it's interesting because then you sort of split the declaration of the function, the type, which is a sort of documentation, especially if the names of the functions are more informative than f and g, from the body, from the implementation. And if the types and the name are expressive enough, you don't need to read anything that is to the right of the equal sign. So I do like this. I have to say I'm kind of addicted to this. Anyway, these two functions can be composed. How can they be composed? Well, I could compose them into a function that looks like this, where it takes as input the enumerable, returns as input a boolean. Let's call this function f then g. And what do we take as input? Well, we take as input L, which is, the list, but then we just call g with f of L. There you go. So basically we take L, give it to f, and then pass the result of f to g. There is a way, this is so common, this is like the basic concept of pipelines. So this is a pipeline. F then g is a pipeline. And you can keep doing this. How can you keep doing this? Well, you could say that there's a way to take, let's call this age, takes as input a value and simply flips it. So the not of x. So if x is true, then we get false. If x is false, then we get true. And we could say f then g then age, and we can say age of g of f of l. Okay? These pipelines are super common. So let's make this pipeline concept a little bit more generic. Let's define a static class. This is a very neat trick that allows us to define methods that are called extension methods in a static class on top of an existing class in order to extend it. let's call this function extensions or func extensions. Then we add a public static func input and output. Let's call this then. Then is generic. It's a generic static method. Generic in two types that we don't really care what types these are. Input temporary and output, temporary or intermediate, even better, okay. So, because well, we can stitch together functions with any types as long as the output of the first is equal to the input of the second. So we don't care what they are, so we simply say input is the input of the first, intermediate is the output of the first, but also intermediate is the input of the second, output is the output of the second. Because we don't really care about whether or not we're dealing with integers, strings, etc. So we are introducing these generic parameters to the then function, so that we don't have to bother with defining a new one of these for enumerable of int, bool, etc. So we build an implementation that reflects a structure, abstracting away, generalizing away from the details of the specific types, because we only care about the structure of the container, the function in our case, and not the content, which are the type arguments. Okay, then we mark the first parameter as this, and let's call this the first function. And the first function will take as input and return the intermediate value. Then the second function takes as input the intermediate value and returns the output. There you go. Now we have to return, as promised, a function from input to output. So we return a function that, first we get as input the input. We call first of I, and the result of first of I, which is intermediate, we pass it to second. The compiler is happy. I'm dealing with generics, when the compiler is happy, usually you can sort of rest assured the program probably will work, because generic code tends to have this magical property. If it compiles, if it compiles and it's immutable, usually it works. Alright, now for more magic, this f then g then h, I would advise you to sit now in a place where if you faint from the excitement, nothing happens to you and you don't hurt yourself. So you've been warned. F, then G, then H. And what is the type of F, then G, then H? It's a function from enumerable of int to bool. Okay. And well, let's actually call it F, then G, then H. Let's pass it, I don't know, 1, 2, 3. Okay, let's see. So the sum of this is, okay, the pipeline itself is nonsensical, obviously, but yeah, I mean, this is the side effect of having slightly abstract examples. Okay, so we have 1, 2, 3. They're going to be added together. The result is 6. We check if it's modulus 2. The answer is true. And then we flip it, and so we get false. Yay, we get false. Let's run this with the debugger. Now, okay, so funnily enough, the target of this contains first and second of the first target are again first and second, because yeah, first and second are the closure of this lambda here that has been created, and obviously first and second need to be stored somewhere in the closure of f then g then h. So basically f then g then h in its closure needs to store f, g, and h, because yeah, it needs to know which functions it's actually supposed to run. And if you keep going, at some point the target will simply tell you, well, no, this is the function defined. Yeah, you can see it here, main b00. So this is basically saying at which address in the main program. So this is one of the actual functions that we had. Very cool, very exciting. Okay. And of course, you can imagine that, yeah, okay, this is a terrible name because it shouldn't be F then G then H, but it should be something like flip sum is even or something like that. Let's, you know what, let's simply call it my pipeline. Okay. You can also compose a pipeline dynamically. So if the output of the pipeline is the same as the input of the pipeline, sometimes you have a function from, let's say, state to state or context to context, then you can actually add post-processing steps dynamically. For example, the middleware system of ASP.NET is kind of based on basically this principle, or a principle very similar to this. So we have precedents, and something that's also kind of fun is that you don't necessarily need to define all these functions. So for example, well, the last one in particular, the last one doesn't necessarily need to be specified, so you could also pass it as a lambda, and this would also work, and also this one you could pass as a lambda. Well, you can pass them all as a lambda, and depending on whether or not you want to reuse them. And let me see how to have this as a lambda. Well, of course, we can't just write things like this because then the type of value is completely unknown. Let me see if this hint is enough. Let's see. No, that's a bit unfortunate. So why is it complaining? You cannot put it on a lambda expression right away. So the whole lambda chain has to start with a variable somewhere. So the first one has to be a variable. Other languages are actually slightly further than this. Namely, I think TypeScript can do more with lambda expressions. Like you have the lambda expression, and you start playing around with it, directly. All right. Now we're going to add time into the mix. So functions. So this type func, especially when we say, let's say, func of string f is whatever, denotes, for example, yeah, whatever, not a very exciting one. Oops, no, let's change the name. F1 is a piece of code that returns a string. Now, we could imagine that this happens very quickly. Usually, on average, unless you have a very complicated algorithm, a function that returns something will be, for all practical purposes, sort of instantaneous. Or at least, even when it takes time, there are no interruptions. So the code just bam, runs from start to end on your CPU, one instruction after the other, until the result is actually computed. Sometimes, though, we have the equivalent of a function which runs over a much longer period of time. And this is called a task. Of course, this doesn't work anymore. What is a task? Well, a task of string is, in a sense, very similar to a function because it will compute, in our case, a string. We could also combine, by the way. So we could have a function that takes as input an integer and returns a task of string. And the task of string is an asynchronous object, meaning that it will take its sweet time, potentially, could be very quick, could also be very slow, to compute the string in question. String, person, list of int, whatever. The task is a generic asynchronous container. I also still like this metaphor of saying, okay, all generics are in a sense containers, that is, they literally contain data. The question is, when do they contain data? Do they contain it right away, like an array or a list? Do they contain it in a specific order or structure? That would be a dictionary. Do they contain it virtually, that is, they calculate it, that would be the func, or the task, do they contain it virtually, that is, they calculate it, but in order to calculate it, they need to wait, potentially, for some external sources of data. Reading it from the hard disk, from the hard disk is basically another component. It's a lot slower than calculating, usually reading big stuff from a file. Reading it from another service, waiting for the slowest connected system of all, the biological user who has to type something in from on the keyboard. So these are all examples of tasks. These are all examples of tasks that calculate a result and also need to wait for external entities to provide the whole result or parts of it. And the coolest thing is that because tasks are slow, we can run them in parallel. We can run them concurrently. All right. So, we can actually define a function as async, because obviously there's a relationship between tasks and functions. That's why we started with functions. By marking it with a special keyword, async, and we'll see also the counterpart of async, which is await. So for example, we could say that we have a write_int function which returns a task, because again, as we said, anything asynchronous returns a task because we wrap this operation in a task object that we can then wait upon. Then let's say write_int, which takes as input an integer and writes it to a specific file. I don't remember these things by heart, so sometimes I need to check out my own notes. And then what do we do? Well, we can call file.write all text async, and well, we're going to write this to file.txt, and we write n.toString. Okay. No, I really don't want this. And we return this. Oh, what a disappointment. Why not? Write on text async returns the task. Oh. Okay. Wait a second. No. Let me actually do this in steps. Okay. So first of all, let's run it this way. So write on text async doesn't write the text directly, but rather it returns a task, and then you have to wait for that task to run. So now I could say write_int, and I have to wait for it. So I could say wait all, and then I could, I don't know, create an array with just one instance of this task. And wait all, what it does is simply, well, actually stops the program and wait for the tasks. Okay, let's run this. Okay, the program is actually running, very good. And now let's take a look at file.txt, and we can actually see that there is just a number 10 in the content of the file. Okay, not very exciting. And if you want to see it better, perhaps, well, there you go. There's the file with 10 inside it. All right, very good. Now, here, what we're doing is we're returning the task. But when manipulating tasks, there is so much more that we can do. And for this, the async and await keywords have been invented. So when we mark a function as async, basically, yes, we're returning a task, but the task is composed through a series, as a sort of state machine is created in the background by the compiler, and the state machine can also be very sophisticated. And by awaiting, we're actually saying, okay, the task that is being created for us implicitly in this sort of state machine, at this point, the first thing it does is it runs the write all text async task, so as a sort of, you could say, sub-task, and only when this is done, we continue to the next instruction. The cool thing about this is that we can compose multiple tasks together sequentially or at the same time. Let me show you what this means. So let's say that we want to write a number n onto a bunch of files. Okay, so I could say for each file in files, okay, and instead of here writing to file.txt, we write on this file. So now these different awaits, it kind of looks like we're writing normal code here, but actually what's happening is that we have one task for every file we want to write, and these tasks will be waiting for each other. So the first one is run, then we go back to the function write-int, then we go to the next, we go back to the function write-in, and so on. So this is a way to sequentialize these tasks. So, well, at this point, let's say that we want to have this in file.txt, but also file.markdown, yeah, okay, this is really silly what I'm doing here, but it doesn't matter, you just get the gist of it. And then if we run this run this program, .run, well, okay, and now we get, you know, file CSV, file MD, file TXT. Okay, we'll have to remember to clean this up. These are really garbage files. Okay, but this is where it becomes very exciting. Well, you could also say, but wait a second. You can write files in parallel and just let the operating system simply, you know, deal with it. So we could say, okay, we have a bunch of tasks, and well, so for each file, say, okay, take this file and write all text async. All right, let's put this to 100 and let's run this. And files haven't changed. This is the interesting thing about manipulating tasks. Just the fact that you create a task, like write all text async, if you don't run it in any way by doing wait all or await on it, task ain't going to happen. This is actually quite interesting. So this task here, it's like a box, like a Schrödinger's cat box that doesn't contain the result until you actually open and check it by awaiting the task. So creating the task doesn't run it automatically. And this is a bit of a slightly different way of reasoning, if you will. So now we take this, well, this is an enumerable of tasks, and now we say task dot wait all, when all, and now look at this, this is actually super exciting. So task when all takes as input an array of tasks. So I'm just going to turn this into an array right here, and notice that I get a warning because this is saying, oh, wait a second. So well, this is really not a good pattern, because write-int, it's an async method, so it has this special power that you can actually await a task. But if we don't await the task just starts on the background, and then it's kind of unreliable. That write-int basically goes to, let's say, line 8. So console.write line done, but actually the tasks aren't done because we have to await for the tasks to actually have been performed. And what does when all do? When all says, okay, start all the tasks in parallel and don't consider line 7 done until all the tasks have been completed. The very cool thing about this is that if you have multiple tasks, for example, one task that has to talk to a web server, one task reading data from the database, one task writing something to a file, well, they're all using different resources, so you can actually run them in parallel. And if all these three operations, the database takes 2 seconds, writing to the file takes 1 second, and talking to the external server takes 10 seconds, well, the whole runtime will be 10 seconds, because it's still going to be the runtime of the longest task, but it's not 10 plus 5 plus 2. I think it was 5 and 2, whatever. So we run things faster. Of course, if you're writing 3 big files on the hard disk at the same time and it's the same hard disk, then that's a bottleneck, so this only really properly works when you have things that actually can run in parallel. But if it is hard disk, network, and database, yeah, most likely you will actually get some significant speedups. So, very cool. Now, let's run this. And let's say, let's print file.txt, and now we have 100, and also file.md, also 100, and file.csv, and that is also 100. The task parallel library is really exciting. Okay, I don't remember actually if you can await. Yes, you can also await at the top level. So the main program happens to be a sort of big async await thingy. And yeah, async await makes it possible to basically treat these tasks as instructions, but whenever something is async, then yeah, you can await inside it, and obviously if something is async, in order to run it, you have to await on top of it. It's kind of, no, I don't want to say it's kind of like contagious sickness, because that's like a terrible metaphor. No, but as soon as something starts being a task, then everything has to await on it. So you can't really properly escape tasks unless you do, like I showed, task wait all, but that's actually busy polls, so that's actually not a particularly brilliant idea in practice unless you can't avoid it. Okay, now that we know that our files have written an int, we could read the int back. So you could say, okay, task of int read, or let's say no, we read all the ints. So int array, we can do whatever we want actually. And actually, oh wow, no, not the int obviously, because the int we're going to have to read. And how do we read content from a file, for example? Well, the content of the file could be, whoa, what is happening? File.read all text async. And by the way, you might have noticed that we have the async and non-async methods. The async methods are much better because they allow you to, if you run the non-async method, it's fine, you'll be fine, but you're basically blocking your program's ability to run an operation that might be slow in parallel with other operations, making it better for the end user. So in general, I'd much rather read and write files, perform calls to other APIs, etc. asynchronously. Okay, well, no, we have multiple files, so actually we have to do the same thing we did before. So for each file, we call read all text async. Well, we're not really calling it, actually we prime it, you could say. Yes, we sort of, yeah, that's actually kind of nice. So we prime it, and then var, so these are the content tasks that will actually get the content. Then we could say contents, kind of ugly, but whatever. Task dot, oops, when all of int, and then content tasks dot to array. Why is it unhappy? Oh, yes, of course, these are not ints. How silly of me. Okay, so this would be a string. Now the contents are, well, this is a task of string array. But if we await this task, then contents is all of a sudden a string array, because now this will contain, so basically, okay, what does when all do? It takes every one of these tasks, which are reading content from a bunch of files, run each one of them in parallel. When they are all finished, then we take all the results, and of course these content tasks have to be an array of tasks of the same type. So look at the signature. This says, okay, when all of t result, this is the type of the result of the task, then the tasks are an array of task of t result, and then when it kind of switches the array and the task. I don't want to say something too mathematic-y, but it's kind of funny because array is a generic type, task is a generic type, and this is the commutation of the generic types, which is actually kind of awesome, because this doesn't happen with all generic types. But tasks, if you have the task inside an array, you can actually flip array and task, and that's very beautiful. This commutation is uncommon. Okay, anyway, now we have the results, so we switched it. We had a task of results, and now we have well, we have the result array because we're awaiting. So awaiting allows us to actually see the results, and then we can say, okay, we just return contents dot select, and then int dot parse. We're going to be a bit optimistic here, and we're just going to parse the results. Okay. Or we could have also said, yeah, okay, this is the string of the content, and then we just pass it to parse, but we can do a so-called eta reduction, very mathematical term, sorry, because it's twice today, but we just pass the function, and the function will be applied. Now I'm not doing any validation, I hope you can forgive it for a moment. Now let's create the files. There we go, and then we can say await read int, and read it from the files. Because the files have the same names, then we should get the same results. Let's start debugging. One of the very cool things about this debugger is that it works. Oh, not saving, not saving the results. More numbers, and obviously the numbers are going to be a not particularly mind-blowing array of 100, 100, 100, but I mean, the example doesn't really matter. We're really focusing on the tasks and how they work. So we see numbers is 3, 100, 100, and 100. Okay, very good. We could make this just a tiny little bit more exciting. So we could say that here we get the operations. So instead of getting this silly number n, we could say string file name int number. Okay, and we could say that for all the operations, here we have the operation, and then operation dot file name, and we write operation dot number. Then at least we can write different, different values on the different files. So we could say file.txt we write 100, file.md we write 200, and file.csv we write 300. Now all of a sudden the sample kind of feels a little bit better. I like this. Okay, now this is just one parameter. There you go. And here, of course, well, we don't want to pass the numbers because in readint we want to be able to read the numbers. So we select, and for each operation we just get the file name. Yeah, okay, whatever, item 1. And of course we need to convert to an array because the function expects an array. Let's run this again. String dot join, joins with a comma, and we pass the numbers. Okay, let's run it. .NET run. And there you go. You see, there's a noticeable delay, I suspect, because reading and writing from files. Oh, and you can also see 100, 200, 300, so also very, very nice. Okay. Of course, now here what we're doing is saying, okay, when a task is done, we get all the contents. The contents are strings, and because we await, we get to manipulate the strings directly, and then we can parse. But actually, we could have gone a slightly longer path, or no, not necessarily slightly, but we could have made this a little bit. Well, how can I say this? We can put the awaiting a sequentialization at multiple levels. So, for example, here what I'm doing is for every file that I want to read, I actually built an async function. So you can see I can put async inside the lambda of the select that's going to transform every item, and now I get the content. Of course, I have to return something. Oh, also need a semicolon here. I could return int.parse of the content. Now I get a complaint here that's saying, okay, when all, when all what? Yeah, when all of int, but actually I don't even need the type parameter, it's guessed correctly, and now this is just an int array contents, which I can return right away. And even though the result is effectively the same, so let's run this and we get, once again, 100, 200, 300, so very good. In the previous version, I was first reading the files, then processing the array of results from the files, which are just a bunch of strings, and converting those to ints. In this case, what I'm really doing is for each file, I have one task that reads the content of the file and processes it in that same task. So yeah, I'm not saying that this is particularly better, there is almost no difference, but sometimes you want to chain, if you want to run some tasks in parallel, you want to make sure that the tasks you run in parallel are actually composed out of a bunch of smaller tasks, because this way the things you run in parallel have a chance to alternate, and so you use your available CPU and memory more effectively. So this creates better performance. Simply, you need to wait less for the whole thing to be done. All right. Now, something else that I would like to show is how to read data from a web service. All right. Now, we create a client, an HTTP client. All right, and then we get a response by awaiting. Oh, look, client, let's get async. What are we going to put in here? HTTP bin.org/get. Okay. Let's just print the response dot content. Okay, let's run this. Okay, there is code. Well, no, not really that exciting. I'm wondering if toString is going to do. No, it probably will not, I guess. Okay, let's run the debugger. But you know, at least something is happening. Okay, we got okay. We have the successful status code, and how about the content? Actually, see this. No, not very exciting. Yeah, we probably had to. We probably would have to read it. Okay. So read string async, which I guess we can await. And let's take a look at the JSON that's coming out of it. And there you go. Now you can see the JSON that has been parsed. And because parsing the JSON, so the JSON came back as a sort of binary blob, and before you parse it into a JSON object, which takes quite some time, so this is not done automatically in the content. So the content is a stream or a task if you want, and then you actually have to await it. You can also see that C# is really super mega smart. Because you can await inside an expression. Sometimes you have to put some extra brackets, and when you put the brackets, you actually get to manipulate the string instead of the task. So when you put the brackets, so if I put the dot here, you see a result status is 40. This is the task because this is the read the string async. But if I put the brackets around it, the compiler magic of C# allows me to access this as the string that will come out of await. The power of brackets around await, this is just a stroke of genius from the C# people. C# people, kudos. This one is really brilliant. I know you know that this was brilliant, but I'm happy to tell you. Like one of the nicest implicit monadic binding operators in the history of monadic binding operators. That's good. Now, one thing that I really like is that sometimes we can simulate delays. And you might wonder, okay, usually I want to make my programs faster. Why would I want to make my program slower? Well, first of all, let's see how. I could say await delay 1000. Now there is an extra delay of 1 second. And you might wonder, okay, like, isn't this the stupidest function ever? No. Very often, when running a program locally, the program is super fast. Maybe the web server and the database are literally running on your local machine, and you want to simulate real-life scenarios. So you could say, let me actually package all of this nicely. Let's say that, oops, let's say that all of this was just a big function. Okay, so async call my API, whatever. Oh, and this returns task of string. Okay, so it's just a little function that calls an API, and then we say, okay, await call my API. All right. So functioning the program is very similar to the previous one, but and this get endpoint is actually pretty fast. But we want to simulate a system where we have much bigger delays, and those delays are a little bit random. Why? Because we want to, for example, test that if there is a front end that we're building on top of our .NET backend, for example, we simulate that this system wasn't available or was intermittently slower because we found out that the system sometimes has delay when, I don't know, an export is running in the background, whatever. So a very neat way of doing this is to say, okay, create a new random number, get to the next double, which is going to be between 0 and 1, multiply by, let's say, 2500, and add 500. So what is this going to do? This needs to be cast to int. Okay, because we don't really care about the fractional part for milliseconds. So this will be a delay between 500 and 3000 milliseconds. So between half a second and 3 seconds. Or we could say that, and obviously you can make this as you can also create more complicated probabilities, like you could use more complicated formulas to have a non-uniform probability, but in this case the probability of 500 milliseconds and the probability of 3000 will be the same, but in reality you might say you want more often to see the faster call than not, whatever, but at least whoever is building your front end will be able to see at least half a second of, for example, the loader or animation transition, etc. Whereas if you have an API that is done like this in 20 milliseconds, you will barely be able to see transitions, but then your end users will, and it will be a part of your code, how your application behaves when there is slowness in the backend. Well, that will have not been tested properly. Yes. And I think this is a very neat trick, actually, and you could say, yeah, now it's taking longer, you see? Now it's taking longer. Now it's also taking longer. Now, okay, yeah, I mean, I have no idea. Now, wait a second. You know what? Let's also test that what we're doing is actually correct. So, oh, wow! Okay, that was impressive. Ooh. Sometimes it really guesses. Sometimes it's like embarrassing, but sometimes it really guesses very neatly. Okay, and here at the end we're going to write stopwatch dot elapsed milliseconds. There you go. I really want to see how long it just took. So there's also the start time of the .NET itself. So now, oh, now it's between 10 seconds, sorry, 10 and a half seconds. Oh, okay, we just got unlucky, so 9.93 seconds. I really want to see another number than 9,930, because that would be a major bummer. Okay, that's slightly suspicious. Okay. This is a constellation what are the odds that we will get the fractional part of the second to 0.33? I have no idea. Very interesting. Okay, okay. So this is forcing us to acknowledge that, okay, or at least, you know, if there were a loader animation, okay, now it was faster, but now we get, for example, our front-end team to be able to occasionally test, okay, what does their transition look like when the server is being very slow, for example. So indeed, quite cool. We can also, and this is also quite cool, we could say that we also let our system occasionally fail. So look at this. Look at this. So there is another method, which is when any. When all and when any are almost the same, but also not quite. So when any will trigger when any of the tasks given triggers, whereas when all waits for all of them. So I could say, okay, wait a second. So okay, so async actual call, and now here I can put, okay, this is a task of string, okay, So let's say that I want to be able to inject some code that sometimes tries to work everything, okay? And here I say, okay, when any, and now I put here the extra code. Wait, why is it not happy? From task of string to string. I'm mildly confused about this. Okay, so when any takes as input a task, in our case, an array of tasks of strings. Let me see. Bar tasks. What would the type of tasks be? It would be an array of tasks of string. Okay. So funny. Yeah, the problem. Okay, so the problem is that when any, no, it returns just one string. Okay, so let's pass the tasks and convert task of string to string. Now, this is a task of this is an array of tasks of strings. And let's see what the result is. Wait. All right. Look at this. When any gives the task that completed back. So we actually have to await twice. Kind of ugly, but okay. Very good. So we have. All right. So, and it's kind of funny that you get to see that you can get stuck sometimes. And when you get stuck, c'est la vie. Just take a look at the available sources of information and just reason. Okay. Then this is the broken call, and the broken call will wait. So basically, they run against each other, and one of them is going to win over the other. And in the case of broken call, I simply return error message. Okay. And now if I create here an array with the actual call and the broken call, I don't know which one is going to win. And I have created a really interesting situation where basically I have two calls, and I can test the fact that my calls will be very unreliable in terms of how long they take, and also they will also be quite unreliable in terms of what result do they give. Because, well, these two things are basically running against each other. The first that triggers kills the other. Okay, now I see that the broken call hasn't happened yet. Yes, so there you go, pop, error message. And yeah, this is a very neat way of simulating all sorts of interesting scenarios by means of tasks. So yeah, very cool. Also, needless to say, what can a task return? Anything. So you can have a combination of functions that return tasks, tasks that return functions, etc., depending on the domain, depending on what you need to represent. So you could have something that you could have a task that actually selects an operation that further requires some extra parameter in order to decide what to do. All the things we've seen so far, polymorphism, records, functions, tasks, generic collections, can be put together. And these are the true sort of composable Lego blocks that we get to use in order to build our dynamic systems and architectures. Exciting, isn't it? All right. And yeah, so, and what we've seen so far, is we have generics for building collections and actual boxes containing data, more or less arranged in all sorts of configurations. We can use generics to represent operations like functions, and also concurrent and slow operations like tasks that we can also compose together. It was also funny because we have also seen two ways of composing functions. On one hand, with the then operator that simply says do a function and do the next, like a direct pipeline. And also async await are a way to create sequential pipelines, but then when all and when any make it possible to fork the pipeline and run things in parallel in different ways, so actually quite exciting. And now, armed with all of this power, we will start to write our own generic classes and methods. So let's do this.